So our third component of acids and bases to consider water. Water we know is amphoteric. Being amphoteric, it acts as both an acid and a base. It's important because water is going to be found in lots of organic reactions and lots of biochemical systems, so it's important to consider. Okay. Being amphoteric, we know it's going to act as an acid, it's going to act as a base. Acid definitions are proton donor. Base definition, lone pair donor. Okay, lone pair proton acceptor, whereas this second one is a lone pair acceptor. So obviously contrary definitions as you would expect. So we draw out our water molecule over here and give it our lone pairs of electrons. We can see here we have our base as a lone pair. And over here we have these hydrogens, which can be our protons to donate, which is our acid definition, and this, which is our base definition. And if we look at that from our perspective, here's our water. We're going to react it with HCl. The oxygen with its lone pairs of electrons is going to react with the acid like so to give us H3O plus Cl minus. Here we see the lone pair of electrons being donated. Here it's acting as a base because it's reacting with an acid. And here we have our conjugate base and the hydronium ion, which is our conjugate acid. Okay, that's our hydronium ion. Alternatively, if we look at this from a different perspective with the water, we react it with ammonia. You can see that the ammonia picks up a proton from the water and breaks the oxygen-hydrogen bond. The electrons are donated in the opposite fashion. The result of that is to form OH minus plus NH3 plus, NH4 plus. So now this is our base. More importantly, the water is acting as an acid, and as it acts as an acid, we form this conjugate base, and the ammonia forms the respective conjugate acid. So that's important to remember as we look at these reactions. If we've got water, we also want to think about, well, hey, we've got alcohols. These are also potentially amphoteric, depending on the conditions. We have the oxygen with its lone pair of electrons to act as a base, and the proton here to act as an acid. Obviously, if we have carboxylic acid, we know that that can dissociate like so, because here we now have the acid with the proton to donate, and as this proton donates, we form this conjugate base here, like so, which can be stabilized by resonance. We want to remind ourselves of the resonance when we have the fact that the allylic relationship exists. So we have this as our intermediate. Okay, remember we've got the proton as well. So that's our carboxylic acid. And then if we take a broader picture, we're looking at biological systems and sulfuric acid. We just want to remind ourselves that we've got H2SO4 in equilibrium to give us HSO4 minus plus H plus, which is in equilibrium to give us H plus plus SO4 2 minus. So again, here's our acid, and again we have a proton donated, and then we can donate a second proton here to give us various conjugate acids and conjugate bases. If this is the acid, then this is the respective conjugate base. And if this then is the acid, this is its conjugate base. So it can get complicated. We have to recognize the reference that this is the conjugate base reference to the sulfuric acid, but this is an acid with reference to its conjugate base of the sulfate anion. In addition to that, we can do the same thing with phosphoric acid and phosphates, which are going to be more important in biological systems. We've got this plus H2PO4 minus, which is in equilibrium to give us H plus plus HPO4 2 minus, which is in equilibrium to give us H plus plus PO4 2 minus. So again, this is important in its relationship with ATP and ADP, as we have liberated